Good day, everybody, and welcome to Night Chemistry. Tonight, we're going to be talking about 4 key factors that affect reaction rate. And one of them we've actually already explored, the concentration of reactants. So remember, the greater the concentration of reactants, the more collisions there are between the potential reactants. The more collisions there are, that means there's more of a chance they'll overcome that activation energy barrier, make products, so more collisions means a faster reaction. So now what we're going to do is we're going to explore how the physical state of the reactants will affect the reaction rate. Then we'll look at temperature and presence of a catalyst, and we'll see that we can actually modulate the value of our rate constant K. So with that said, let's take a look at some videos that showcase the importance of the physical state of reactants.
Lead iodide as one of the products. When the reactants are mixed in the solid state, this reaction can only occur in areas where crystals of the 2 reactants are in direct contact, as this is the only place where the collisions between the lead cations and iodide anions necessary to form the yellow product can occur.
So here what we're doing is we're adding together 2 solids. We're adding together potassium iodide and lead nitrate, I believe, some sort of lead. And we're trying to make lead iodide, which is this beautiful yellow salt. So as we're pouring these 2 things together, let's see what happens.
Since the ions are quite immobile in solids and the crystals are still, the frequency of these collisions is very low and no observable reaction takes place. The sample remains white for days.
For days! That's a slow reaction. Let's see if we can speed this up somehow.
Placing the sample on a shaker increases contact between the solids, and friction caused by the constant motion of the solids leads to a slow scraping of ions from the crystal surface. The freed ions combine, slowly yielding the yellow product. The reaction rate is limited by the speed of mechanical mixing.
Isn't that a cool looking product? Okay, so here what we're going to do is we're going to pour our 2 salt reactants into a mortar and pestle, and then we're going to try grinding them together.
The mixing can be made more efficient by grinding the crystals in a mortar, making them smaller and increasing both the contact area and the rate of ion detachment from the surface. Now the mixture turns a deep yellow more quickly, as lead iodide is generated much faster.
Cool, but can we make this faster? Let's see.
If drops of water are added to the mixture of solid reactants, both salts dissolve quickly and the solvated ions react on every collision in the aqueous phase, immediately producing an insoluble lead iodide product. For all practical purposes, the rate of dissolution of the reactants controls the rate.
So here, because we're dissolving it into the aqueous phase, now it's no longer confined into where the position of the solid crystals. So by turning aqueous, these ions are more readily able to interact with each other. Therefore, the reaction goes much, much more quickly. Additionally, if you start with aqueous solutions of these 2 and pour them together, you will get that yellow precipitate almost immediately. So to summarize what we just watched, here's the reaction: lead nitrate reacting with potassium iodide to form the yellow precipitate lead iodide. When we push together these 2 solids, not much happened. Not very exciting at all. If we grind them together or we mechanically mix them, then we give more of an opportunity for collisions, and we introduce in some energy, some kinetic energy, and that's okay. It becomes a little bit faster, more surface area contact, faster reaction. But can we do better? What if we dissolve them in water? Then they're free to move about, combine with each other, and form a precipitate. So, whoa, we got that bright yellow precipitate really, really quickly in those scenarios. So, take home point, the phase of matter matters. Now then, how does temperature affect reaction rate? We already discussed this from a qualitative standpoint. We know that if we increase the temperature, then we have more kinetic energy. More kinetic energy means higher energy collisions. Higher energy means more of a chance of overcoming that activation energy barrier and making a product. So here we have our Boltzmann distribution, and we see if we compare between 400 Kelvin and 600 Kelvin. The 400 Kelvin curve, if this is our activation energy barrier needed, the threshold needed for a reaction to occur, there's only a wee little amount of the molecules that actually have enough energy at 400 Kelvin. At 600 Kelvin, however, look at how many more molecules have that necessary energy. So increasing temperature skews the Boltzmann distribution more toward the right. It means more higher energy molecules, which means a faster reaction. So now what we're going to do is actually take a quantitative look at this. Introducing the Arrhenius equation. Before we looked at our fraction of molecules that have a certain energy level, and we said that it was proportional to e to the power of negative activation energy divided by RT. So since that fraction is proportional to the amount of molecules that have enough energy to overcome that activation energy threshold, that means that it is proportional to the rate constant. So if you have twice as many molecules that have that energy, then you're going to have a reaction going twice as fast. So we can represent K as a function of both activation energy and temperature. Introducing the Arrhenius equation, part 1 of 3. There's multiple versions of this we're going to use. So our generic form is K is equal to A, and then our constant E, Euler's constant, 2.71 something, 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 to the power of negative activation energy divided by RT, where K is our old friend, the rate constant. E sub A, also an old friend, that is the activation energy. Usually activation energy is reported in kilojoules because it's just more of a, it gives us a more user-friendly unit for reporting these numbers. T is our temperature in Kelvin, very, very important. Always plug in Kelvin. R is our gas constant. If you plug in kilojoules, you want to use 0.008314 kilojoules per mole Kelvin. If you use joules for activation energy, 8.314 joules per mole Kelvin. Either works, just make sure you're consistent with your units. Finally, we have something called A. A is called the frequency factor, and it's in essence a measure of the probability of a successful collision. We'll see ways that we can modulate A in just a little bit using enzymes and catalysts, but basically it is a measurement of, are these molecules properly oriented? What is the chance of them actually having a successful collision? So now we're going to quantitatively evaluate how temperature affects reaction rate. Mathematically, what happens as temperature increases? And what I mean by mathematically is we can see here that temperature is in the denominator of the exponent. Moreover, we can also see that our exponent here is negative. So that means as temperature increases, that means the denominator increases, which means the magnitude of our exponent gets smaller and smaller, gets closer to 0. Since it is a negative exponent, that means the greater t is, what's that going to do? It's going to bring our exponent closer to 0. It's going to make it more positive, which means that if we increase if we increase t, k will also increase from a purely mathematical standpoint. So the magnitude of the fraction gets smaller. The exponent therefore gets less negative. Therefore, k will increase. Okay? From a chemistry standpoint, why does increasing the temperature make for a faster reaction? Well, we've already looked at this. There's two main reasons. First, more kinetic energy means there's more energy in the molecules, which means they're bouncing around more quickly, which means there's more collisions. But also, what do we know about those collisions? They are higher energy collisions as well. So for these reasons, chemically, k will increase. This equation up here shows this mathematically. Okay. Also, want to keep in mind that for reactions, for all reactions, k is directly proportional to reaction rate. So if you double k, that means the reaction rate doubles. If you triple k, that means the reaction rate triples, because k is always a constant that goes at the beginning of our rate law. So whatever you do to k, the same thing is going to happen to the rate. If you double k, the rate doubles. If you triple it, the rate triples, et cetera, et cetera, et cetera. This is independent of the concentrations. This is actually adjusting our rate constant. And then we have a graph here of the value of K as we increase temperature. And you'll notice that this graph gets exponentially larger. So as temperature increases, whoa, look at that spike here. Look at how drastically this increases. That's the sound it makes as it gets hotter. It's exponentially larger with temperature. So is there a way that we can maybe see the difference in K at 2 different temperatures? Maybe. I don't know. Actually, lol JK, I do know, and that's what we're going to do now. So, introducing the Arrhenius equation remix. What we're doing, and I'll show you a derivation of this equation in just a little bit, but we have this equation here that allows us to compare the relative rate constants, so K1 versus K2, at 2 different temperatures, T1 and T2. So a few things that I want to point out. Remember, K is directly proportional to rate. So what this means is not only does this show us the relative value of K at 2 different temperatures, we can also infer that that's the difference between the rates. So if K is 5 times as large at one temperature than the other, that means the reaction is going to be going 5 times as fast. Okay? So now let's work out a mathematical, let's actually work out a example problem. So let's say an important reaction has an activation energy of 55 kilojoules per mole. Most reactions fall somewhere between 20 to 200. That's not a definitive rule, but just in general, most of them fall into that category. How many times faster is this reaction at 100 degrees Celsius than at 0 degrees Celsius? The most important part about this, because this is a little bit of a ghastly equation, we've got natural logs, we've got parentheses, we've got variables and denominators. Oh no, it's okay. The most important part is being organized. So always start these problems by declaring your variables. Then it's algebra city, population U. And then you'll be going from there to domination station. So what I personally like to do is, generally speaking, these questions are usually always worded, how many times faster is it at one temperature than another? Because saying how many times slower or something it doesn't make as much sense. So generally speaking, the question is how many times faster is it at one temperature than another? If that's the case, that means that since we know that reactions will always go faster at higher temperatures, that means that we want K1 to be the higher rate constant, because we want to know how many times faster K1 is than K2. So that means that we want T1 to be the higher temperature. So whenever I do problems like these, I always start by writing out T1, so the higher temperature, and then I calculate in Kelvin. Remember, you can take degrees Celsius and just add 273 to it. So it's 373 Kelvin. T2 is our lower temperature, 273 Kelvin. Nice. And now we're going to take our Arrhenius remix and we're going to plug in everything that we know. So I know that our activation energy is 55 kilojoules per mole. I'm going to plug in the according value of our gas constant, 0.008314 kilojoules per mole Kelvin. Also want to point out there's lots of different versions of the gas constant. Previously, when you look at PIVNERT, you look at 0.08206 liters atmospheres per mole Kelvin. We're not using that one here. We're dealing with energy. So we want the 8.314 joules or the 0.00834 kilojoules per mole Kelvin. Then in the parentheses, we have 1 divided by 273K minus 1 divided by 373K. So I always like to say, don't be a calculator superhero here. Don't try to throw everything into your calculator and solve for this in one fell swoop. First thing I would do, get rid of those 1 divided by temperatures there. Get rid of what's in the parentheses. So if we do 1 divided by 273 Kelvin minus 1 divided by 373 Kelvin, we end up getting 0.000982 Kelvin to the negative 1. Cool. Now we're going to multiply that by the 55 kilojoules per mole, and we're going to divide that by the 0.008314 kilojoules per mole Kelvin. So then kilojoules, moles, and Kelvin all cancel out, and we're left with 6.50. At this point, how do we get rid of that natural log? Not with an x, but with Euler's constant. So we'll do e to both powers, and voila, we end up getting 663. So that's the ratio of how many times greater K1 is than K2, which means that this reaction is 663 times faster at 373 Kelvin. A general rule of thumb, not necessarily tried and true, but for estimating it kind of works, is that reaction rate tends to double with about every 10 Kelvin. So finally, presence of a catalyst. How does a presence of a catalyst end up speeding up a reaction? Activation energy makes a big, big, big difference in the rate of a reaction. So now what we're going to do is look at yet another form of the Arrhenius equation, and it is right there. The natural log of the rate constant K equals the natural log of our frequency factor A minus activation energy divided by RT. Is there an important graph we can make out of this? Now, you may recall that I said previously that there are 3 golden graphs of kinetics. There is, for first order reactions, the natural log of concentration versus time. For second order reactions, there is 1 divided by concentration versus time. And for our third and final one, what we're going to do is look at this remixed form of the Arrhenius equation. Now, our friend, the graph enthusiast, don't know if it's the same one, maybe it was Arrhenius, I don't know, came along and went, ooh, look at this equation, because if we get a little clever here, we're going to throw in this phantom 1, because multiplying anything by 1 doesn't actually change the value of the equation. And now if we look at this, we actually get y equals mx plus b. Slope-intercept form yet again. So is there a way that we can turn this into a graph? Yes, we can. And it's arguably one of the most important graphs in all of science, because activation energy is a key property of reactions. And this is how activation energy is found for the hundreds of thousands of reactions that are studied out there. So what we do is, on the y-axis, we plot the natural log of K. On the x-axis, we plot 1 divided by temperature. And you will always get a negative slope. So what does that slope equal to? Hark! We can see here it's equal to negative activation energy divided by R. Cool. So this graph will always be able to give us the activation energy of any reaction. It doesn't matter if it's first order, second order, 3712th order. Doesn't matter. This equation will work. So all you have to do is look at the slope and set that equal to negative activation energy divided by RT. Really, 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 really useful equation. So let's take a look at this Arrhenius plot for a really important reaction. What is the activation energy of this ridiculously important generic reaction? Well, we've got a graph and there's this information that's thrown at us. What can we do? All we have to do is look at the slope. Look no further to find the activation energy. So take a moment and see if you can use that information to figure it out. I'm going to pause dramatically for 5 seconds so you can pause and figure this out. You did it! We look at the slope. The slope here is equal to negative activation energy divided by R. It will always be that way for this graph. So our slope is negative 3,700 K. That's going to be equal to activation energy divided by our constant. So we're going to multiply that 8.314 joules per mole Kelvin through, and we're going to get negative 30,762 joules per mole. That's equal to negative activation energy. So the last thing we have to do is just take those negative signs and drop them as if they're hot. We'll multiply both sides by -1. Activation energy always has to be positive. There's like 2 really, really niche examples that have been found where it's not. Anyway, for all intents and purposes, and for all things Chem 112, activation energy will always be positive. So then we just divide by 1,000 to turn those joules into kilojoules, and we are done. So what is it that a catalyst does? Let's find out. Ooh, dramatic ellipses right now. Factors affecting reactions, part 2, enzymes and catalysis. We've talked about catalysts before. We saw them in mechanisms. We identified them as those chemical entities that are used up in an earlier step and then made again subsequently in a reaction. So there's no net change in them. They're never actually used up, but they help to facilitate a reaction. So what's the definition of a catalyst? Well, it's something that speeds up a reaction without itself undergoing a permanent change. How can it do this? Well, there's a few different ways. It can allow a different mechanism. Cool. It can lower the activation energy. Lower activation energy, faster reaction. Or it can properly orient molecules to react, which is what happens with a lot of the biological enzymes, the catalysts inside our body. More on that in a moment. So here we have a little schematic. Reactants, they want to get to products. There's a pathway that they can do it. Basically, catalysts give them an easier way of doing it. So something to note, that for an overall reaction, if we throw in a catalyst, the thermodynamic state functions, represented by capital letters, like the chemical potential energy change, the enthalpy change, the free energy change, and the entropy change, they're unaffected by the presence of a catalyst. Why is that? They are path independent. State functions, doesn't matter how you get from point A to point B. Doesn't matter what path you took, what matters is where you end up. So catalysts don't change the overall energy change. What they do is they give us a shortcut for getting there. So how can they do this to reaction pathway? They give us a means of lowering the activation energy. So let's say we've got this generic one-step reaction here. What appears to be endergonic. We're going to a higher energy product. So what we can do is create, basically you can think of it as if you have a mountain, you can create a pathway, a tunnel through that mountain, a quicker way of getting to the other side. So if we look at these, generally speaking, catalysts proceed through creating different activated complexes, therefore lower activation energy, and different intermediates. So in this case, in our generic case here, we have a two-step reaction that's facilitated by the catalyst. But if we look at this, our uncatalyzed reaction, look at that massive activation energy. Our uncatalyzed, much, much smaller. Did it change the overall delta E of this reaction? No, not so much. We still have the same reactants. We still have the same products. They still have the same chemical potential energy difference between them. The only difference is how we got from point A to point B. So note here, delta E does not change. Same reactants, same products, same overall energy change, just an easier route to get to the products. So what we're going to do is we're going to talk about different types of catalysts. We're going to talk about homogeneous catalysts, heterogeneous catalysts, and enzymes. And then we'll show a few videos that showcase these things doing, well, their thing. So specifically, we're going to be looking at hydrogen peroxide. Hydrogen peroxide is important. It's used in our bodies. Our white blood cells create hydrogen peroxide to help battle off pathogens. However, it can be toxic. It is toxic if we have too much of it. So we have to find a way of getting rid of it. And if you ever poured hydrogen peroxide on a wound, you know it doesn't just stay stagnant, it bubbles vigorously. The reason why it does that is because it's actually decomposing to form water and oxygen. So, generally speaking, if you just have a beaker full of hydrogen peroxide, it's actually doing this right before your eyes. You just can't see it because it's going really slowly. If we add iodide in, though, what it does is it catalyzes the reaction and it gets it to go more quickly. So here we have our reactions on the left-hand side, we have our products, and instead of having that massive activation energy barrier, it proceeds through this hypoiodite, this IO minus intermediate. So you can actually see this reaction occurring because you end up forming this yellow I3 minus chemical species is formed as sort of a byproduct during this reaction. So if you do this, it turns yellow. We'll see this in a moment. And then the reaction proceeds and it goes much, much more quickly. So we'll visualize this in a moment. But the key point right now is we pour in something, in this case being a homogeneous catalyst, it's the same phase as the reactants. It gives us a different pathway to proceed, lower activation energy, faster reaction. It's much, much, much faster. And in case you're wondering, actually it's about 1 billion times faster. Yikes, that's faster. A heterogeneous catalyst is one that's in a different phase from the reactants. Oftentimes, it might be a surface that can hold together molecules in a certain orientation. In this case, we're using manganese dioxide as basically a chemical scaffolding to hold the H2O2 in place. Then it helps facilitate the reaction, and our oxygen and our water can leave accordingly. As we'll see in a moment, this also makes the reaction go much, much more quickly. Okay, so generally speaking, what we do with a heterogeneous catalyst is we give our chemicals a reactive surface to work upon. So they lower the energy of the intermediates through energetically favorable interactions. So maybe that surface allows for some extra dipole-dipole interactions or some hydrogen bonding. Regardless, it stabilizes the intermediates. Stabilizing them brings down their chemical potential energy, and by doing that, it actually creates lower energy activated complexes, lower energy transition states, more favorable, lower activation energy, faster reaction, et cetera, et cetera, et cetera. So another thing that we talked about before is that rate is affected by surface area and contact and collisions. So more surface area, generally speaking, the catalyst is going to give us a faster reaction. Now then, one of my favorite topics, enzymes. Enzymes are biological catalysts. So what they do is they help accelerate and control reaction rates of important reactions inside of our body. Just some terminology here. So reactants are called substrates in terms of when we're looking at enzymes and what they do. The region where the substrate binds, where it does its thing, is called the active site. So here we have an example of an important molecule called hexokinase. Hexokinase is one of the molecules that helps facilitate glycolysis, the 12-step process that breaks down sugar, glucose, into pyruvate that our body can use then in like the citric acid cycle and whatnot. And what's really, really cool about these catalysts is they are these complex molecules that fold in beautifully precise manners to hold molecules in very, very, very specific orientations that gets them primed to react. So look at this. Like there's that really narrow pocket. It's basically like a puzzle piece. The substrate, the reactant, fits in perfectly into there, and then the reaction can do its thing. Once it's bound, we call this the enzyme substrate complex because they're now coordinated with each other. So you have the enzyme, you have the substrate, it's an enzyme substrate complex. So going back to that idea of having a very precise fit, this gives us something called the lock and key model of enzymes. And basically this model suggests that you have these very specific shapes, these specific active sites that are designed for particular chemical motifs and particular chemicals. So if you have a substrate that fits in, it will lock into place in this molecule and will be able to react. So what do you think enzymes do to activation energy since they speed up reactions? Take a moment. Do you think they lower it? Do they increase it? Or do they do nothing at all? Take a moment, pause, and answer. That's right, they lower it. Lower activation energy means a faster reaction. What do you think they do to the frequency factor A? That's right, they increase it. So they hold molecules in specific ways that prime them to have more favorable collisions to allow for the reaction to go more quickly. So a really cool example here. We have pyruvate carboxylase and biotin. Biotin is an important nutrient, and you can find it in eggs and other things. And it basically acts as like a chemical arm. So you can see this long molecule here. It's called a cofactor because it helps coordinate with this enzyme. It basically grabs CO2 and swings it from one side of the molecule to another. So it's like an arm that grabs onto a molecule and transports it. It's the perfect length to move things from one part of the enzyme to another. That's so cool, is it not? Yes, yes it is. So now let's take a quantitative look at the power of catalysts and enzymes. So we're gonna look at an enzyme called catalase. And catalase facilitates the decomposition of hydrogen peroxide in bodies. So it's an enzyme found in liver. It breaks down H2O2. Again, H2O2 helps fend off invading pathogens, but it's also toxic to our bodies. So catalase is an enzyme that helps to get rid of it. So how does it do that? Well, it lowers the activation energy of the reaction from 72 kilojoules per mole to 28 kilojoules per mole. And I added this in after the fact. It's important to know for doing this calculation, but the human body temperature, the average human body temperature is 310 Kelvin. So how can we figure out how many times faster this reaction is? And we're gonna make an assumption here to make our lives a little bit easier. So for Chem 112, if we have a problem like this, we'll always make this assumption because otherwise things become a little bit too mathematically taxing, but we'll assume that the frequency factor A is unaffected by the presence of the catalyst. Truth be told, it usually is affected because a lot of catalysts, a lot of enzymes work by orienting the molecules properly. So now what we're gonna do is we're gonna set up a ratio. We're gonna set up a ratio of K-cat, our catalyzed reaction, divided by K-uncat, the K of our uncatalyzed reaction. So we're gonna use the Arrhenius equation. And again, here is our Arrhenius equation right here. It is K is equal to our frequency factor A times e to the negative activation energy divided by RT. And all we're doing is setting up this ratio. So we're dividing that by basically the exact same expression here. So I'm going to erase that. When we do this, because of that assumption we made before, our frequency factor A cancels out. And basically now we just have a lot of algebra to do. I recommend, again, don't be a calculator superhero. Don't do this in one fell swoop. I like to individually solve for the exponents and then multiply E by them and then divide the numerator, the catalyzed reaction, by the uncatalyzed. But you can also consolidate this a little bit. We can, using the magic of powers, we can get this more simplified form that we have here. So I'm just going to plug in our values now. And basically what we get is that the ratio of the catalyzed to uncatalyzed reaction is equal to e to the power of negative. And then we have our catalyzed activation energy minus our uncatalyzed. And then we're dividing it by R times T, which is 310 Kelvin. So that ends up being 17.1. We're going to take E to that. And that ends up being 3 times 10 to the 7th. 30 million times faster. Wowzers! That is notable. So here's a depiction of Catalase. Catalase has these cool heme active sites. It's a really, really intense molecule, as a lot of enzymes are. And then you're not responsible for this information in Chem 112. I just think it's fascinating. So enzymes are created through, they've got basically these 4 layers of complexity. There's the primary structure, which is the transcript of amino acids. Amino acids are the monomers that make up enzymes and proteins. So you have the primary structure, which is the individual amino acids that make them up. Then you get a secondary structure, which is largely based on hydrogen bonding. You get these motifs called alpha helices and beta sheets. Then we get this thing called tertiary structure, which describes the 3-dimensional shape. It's created through hydrophobic and hydrophilic interactions, aka like dissolves like. So some amino acids really like being close to water. They have polar groups or they're charged, so they'll tend to go to the outside of molecules and create active sites. Other ones are hydrophobic. There are a lot of hydrocarbons. They don't want to interact with water, so they burrow into the inside of the molecule. And by having this, you end up getting these really precise active sites that fold spontaneously as the enzyme is made out of the ribosome. It's so, so cool. And so here we have an example of a few different amino acids. We have small hydrophobic ones that are just like, they're side chains. All amino acids have an amino, and a carboxylic acid, hence acid. So we have small hydrophobic ones like valine. We have tryptophan, which is large and hydrophobic. Here we have glutamic acid, which is, we'll learn more about acids and bases. That's usually charged at inside the human body, which ends up making it interact more with water. And then we have histidine right here. Anyway, based off of these side chains and if they interact with water readily or not, you get these amazing shapes. It's super duper cool. Behold the genetic code and the various codes that we get from our DNA to our RNA to the transcript of primary structure that we get through for our enzymes. It's just so neat, so neat. Finally, quaternary structure is when you have multiple three-dimensional structures that come together to create a larger molecule. Like catalase, we can see over here. Catalase basically has these large different domains that come together. There's 4 active sites in it. Just really, really neat. One final thing to note about enzymes is they are affected by their environment. They're affected by temperature, they're affected by pH. There's an optimal set of conditions that they function at. So for example, enzymes in our blood function optimally around 310 Kelvin. If the temperature gets too high or too low, then you start messing with the intermolecular forces, and then you end up getting them to denature. pH also, the presence of hydronium or hydroxide in a solution will change these radically as well. And you can check out, there's a video that shows catalase in action. Turns out that if you were to, if you fry liver, so if you make cooked liver, for example, and you try to have catalase do its reaction, it will not work. And that's a fun demo that we do in class. We take calf liver and we show that it can work. You can find that video on your ebook. But then if you cook it with onions and salt and pepper and whatnot, and you throw it into hydrogen peroxide, not so much, because we end up breaking the active site. And if there's no active site, there is no catalysis.